Hi, and welcome to this video on the Laplace transform. So here's the thing, you usually start with the dynamical system, something you want to model in physics, biology, or engineering. You come up with some differential equations, a system of usually non-linear differential equations that describe the evolution of some variable in time. But because these are non-linear, what you would typically do, and we discussed about this last time, is that you would linearize. So fine, you have ended up with a system of linear differential equations in the time domain. But still the thing is that because these are differential, they are difficult to solve. And it's all because of these derivatives you have there, the time derivatives. The Laplace transform allows you to get rid of the derivatives. So you apply the Laplace transform, which I'll explain in a moment, to your differential equations, and you turn them into algebraic equations, which of course you can solve much easier. In fact, these happen to be simple algebraic equations. And then if you really want to solve the differential equation, you can apply the inverse Laplace transform and get your solution. But you can do better often. So instead of solving, you can study the properties of your solution. You can tell, for example, if it converges, if it is oscillatory, and a bunch of other properties without even having to solve anything. And this simplifies things greatly. Right, so what is the Laplace transform? We'll start with a simpler definition, that of a time domain function. Well, this is simply a function f that lives on this half line. It takes in a time t, which is non-negative, and gives you back either a real number or, more generally, if you like, it can be a complex number. Okay, cool. Now, the Laplace transform, the thing is that at this stage, I cannot really explain why the Laplace transform is defined by this strange formula, but I'll make another video to explain, actually, to somehow demystify this weird integral. Let's have a look. The Laplace transform of a function f, which lives in the time domain, a time domain function, it is f of t, is this new function of the variable s, which is the integral from 0 to infinity, here, of this exponential function e to the minus s tau times your function, and you integrate with respect to tau. And this is defined, if it is defined at all, because note, it's an integral from 0 to infinity. It may not even converge, but if we're lucky, it converges for some complex numbers a. S is a complex number. Here's an example for us to understand how this works, really. Let's try to determine the Laplace of 1, the Laplace of the constant function 1. So using the definition over here, this, we'll have, you put 1, e to the minus s tau times 1, well, okay, which is minus 1 over s, e to the minus s tau, and tau goes from 0 to infinity. So this is equal to minus 1 over s. I'll put this outside. The limit of e to the minus s tau, as tau goes to infinity, minus e to the minus s times 0, well, this is just 1. And now the question is, what is this limit? If s were a real number and s were positive, then e to the minus s tau goes like this with respect to tau, and you see the limit is 0. If, on the other hand, s were a real number and it was positive, s would go like this, and it would go to infinity. And if s is 0, well, wait, s cannot be 0 because of this. So we won't even discuss about this case. Now, I'm explaining in detail in another video, a longer video, that it turns out this limit is defined whenever s is a complex number and the real part of s is positive, as in this case. But I want to keep this video short, so if you want the details, check the textbook or check the other video. So this is now equal to minus 1 over s, and this limit we said goes to 0, and we have this other minus. Oops, sorry, you couldn't see this. Minus 1 over s, and we have this other minus here, so this becomes a plus 1 over s. That's it, 1 over s. And this is defined. This is defined for complex numbers s with a real part which is positive. And this was our first Laplace transform. The Laplace of 1 is 1 over s. As an exercise, you can try this at home. Determine the Laplace of the exponential e to the minus 80 or e to the plus 80, doesn't matter, whatever you like. A here, you can take it to be a real number, or if you like, you can take it to be a complex number, as you wish. Now, in the other longer video, I will link it in the description, I'm proving all these Laplace transforms. I'm providing a step-by-step proof. But here I want to keep this short, so let me just go through them. We already showed that the Laplace transform of 1 is 1 over s. It's a function of s, and it is defined for all complex numbers s with the real part being positive. The exponential turns out to be 1 over s minus a. You have e to the 80, it becomes 1 over s minus a. The third one is the Laplace transform of this function here, which is called the Heaviside function with parameter a. Now, this is a very useful function, especially in electrical engineering, because this is your familiar switch at time a. This is time, this is your function ha, this is time a, and at this time a, your function from 0 goes to 1. You flip a switch, you turn it on. So the Laplace transform of this function is e to the minus as over s. I'm mentioning this function and we'll be using it a lot because we have lots of systems in real life, in the real world, that have switches. For example, circuits, right? Or for example, you have a bouncing ball that moves down in free fall, and then it touches the ground, and then it bounces up. Maybe it loses energy there, but now the system enters a new mode. It's like flicking a switch, and so on. The Laplace of sine, now things become a little more interesting. You have a more interesting denominator. The Laplace of sine of omega t is omega over s squared plus omega squared. The Laplace of cosine is similar. It's like this. And the Laplace of powers, also there is a formula for powers. You can put here nu equals 1, 2, 3, and so on. If you put, for example, 2, the Laplace of t squared, which is a function of s, is, according to this formula, 2 factorial over s to the power 2 plus 1 is 3. And 2 factorial is just 2. So 2 over s to the power 3. So you can determine the Laplace transform of polynomials. This is like a table of the basic Laplace transforms you need to know. And then there are more you can find in the textbook. The Laplace transform has some very nice properties that we use all the time. I think the main one we really use in every single exercise, every single application, is linearity. By the way, I wanted to say here that these properties are will be familiar to you because you've seen these properties in the first semester when you talked about the Fourier transform. And if you look closely, the Laplace transform and the Fourier transform are extremely similar. So linearity is number one. Okay, so when you have a function f and the function g, and you have constant parameters a and b, the Laplace of af plus bg, this is a plus here, is equal to a Laplace of f plus b Laplace of g. Right, now be careful. The Laplace of f times g, where f and g are functions, if you multiply together two functions, then you cannot split, you cannot break it into the Laplace of f times the Laplace of g. This is just wrong. So this is property number one. I believe time scaling should be a familiar property from the Fourier transform. So the Laplace of a scaled version of f by a parameter a, where a is positive, of course, because we don't deal with negative times here, is 1 over a times the Laplace of f evaluated at s over a. There is a little footnote here, provided s over a can be put inside the Laplace of f, because the Laplace of f has a domain. Maybe we're not allowed to divide by a, I don't know. So the Laplace, the Laplace of f evaluated at s over a, right? This needs to be in the domain of the Laplace of f. So again, linearity, time scaling, and the last one, the third property, is translation in the S domain. Well, in lack of a better title for this property. It's a formula that gives you the Laplace of a function f when you multiply it by an exponential. And what happens here is that the result is the function f evaluated at s plus a. To give you a quick example about how this can be useful, if you need to determine the Laplace of v to the minus a t times sine of omega t, and I gave you the formula for sine of omega t before, it was omega over s squared plus omega squared. Now you have this exponential here. So what you do is that you take the formula of the sine, of the Laplace of sine, and you do here plus a. That's it. So that's why this is useful, because you can do things like this. Right, I said I want to keep this video short, so that's really it for now. In the next video, we'll talk about how to determine the Laplace transform of functions defined piecewise, and to that end we'll be using, of course, the Heaviside function, which is a switch. And we'll discuss also how to determine the Laplace transform of periodic functions. Thank you for watching, and goodbye.